Alrighty, so we're picking up on page 7 of the chapter 16 notes, talking about how to find the concentration of hydrogen or hydronium ions and to calculate the pH of solutions. And this is going to be different for strong acids versus weak acids. So a strong acid, remember, it completely dissociates. So if HA is a strong acid, this is a one-way arrow. It completely dissociates into hydrogen ions and that conjugate base, the A- ions. So for a strong acid, the concentration of hydronium, or H+, is equal to the concentration of the strong acid. For example, if we have the strong acid hydrochloric acid and it's a concentration of 6 molar. So if we have 6 molar hydrochloric acid, it's going to completely dissociate and we're going to have 6 molar of hydrogen or hydronium ions. So the pH of this solution of 6 molar hydrochloric acid is the negative log of 6, which is negative 0.78. Yes, that is a negative pH. pH can be negative for very strong acids. For high concentrations of strong acids, it can actually be a little bit less than 1. Now, for weak acids, all right, the acid is only partially dissociating, and so we see this two-way reversible reaction. And we know that for reversible reactions, they ultimately reach equilibrium. And so in order to determine the pH, we need to know the concentration of the hydrogen or hydronium ions, and we can figure that out the same way we figure out equilibrium concentrations doing equilibrium problems using an icebox. So that's what we're going to do next. So let's say we have weak acid, generic weak acid, HA. All right, and we have 1 molar is the concentration of HA. All right, so the first thing we'll do with an equilibrium problem is we need to write out the equilibrium equation. So this acid, HA, is going to dissociate partially into H plus and A minus, and then we're going to turn this equation into an icebox. Initial change equilibrium. So initially we have 1 molar HA and we have no product, and it will dissociate, so it'll go down by some amount and the H and A will go up by some amount. So at equilibrium we will have 1 minus X of the acid, and we will have X and X of the H plus and the A minus. All right, so for this equation, we would have an equilibrium constant, a Ka, and it would be the concentration of the products divided by the concentration of the reactants. And we can plug in here that the equilibrium values of each of these are X times X over X minus 1. 1 minus X. All right, so since the Ka's of weak acids are generally very small, Ka for weak acids are usually very small, like 10 times 10 to the negative 8th times 10 to the negative 5th. All right, and we know that if the Ka is small, then we can use that X approximation technique to solve it. So we could simplify, if we're doing the X approximation technique, we can basically cross this out and simplify it as X squared over 1. All right, so that's what we're going to use this method in order to solve these problems. And then to get the pH of this weak acid, we just take the pH of this concentration. So it's the negative log of whatever we solve x to be, and that's how we get the pH. Okay, so if we were to sort of write out these steps, it would be first to write out the equation. If you're asked for the pH of a weak acid, I'll even update this. So if you're asked for the pH of a weak acid, the first thing you should do is write the equation. All right, and you should also get the Ka value, which you can find on a table, and I've posted this table on Blackboard for you. You can also find it in the textbook or just Google. So I'm just going to say from a table. The second thing you do is create your icebox. And you use it to solve for the equilibrium concentration. Concentration of hydrogen ions. And then you use, the last thing is you take the negative log of that hydrogen concentration that you find to determine pH. All right, so now let's try a practice problem. All right, it says find the hydronium ion concentration and pH of a 0.1 molar HCN solution. So the first thing I want to do is write out the equation. HCN is a weak acid. That means it's going to partially dissociate into H+, and the A-, the negative ion, is just going to be what's left, the Cn-. Okay, so now I create an icebox, make this into a table. So I've got I, C, E. Initially, I have 0.10 molar HCN and no product. This is going to go down by X. Each of these will go up by X amount. So at equilibrium, we will have 0.1 minus X, X, and X. I also need to look up the Ka for HCN, and I can look it up on a table and find that it is 4.9 times 10 to the negative 10. That's the Ka. I got that from looking it up on a table. Okay, so now I can set up the equilibrium constant expression. Remember, it's products over reactants. All right, so the Ka is 4.9 times 10 to the negative 10. And the concentration of H is X. The concentration of Cn- is X. And the concentration of the HCN at equilibrium is 0.1 minus X. I'm going to do a little simplifying here. So for 1, X times X is the same thing as X squared. And we're going to use the X approximation technique. Since this Ka is so small, we're going to say that this X is negligible, that when we do 0.1 minus X, it's going to be so small, it's still just going to be 0.1, that the X that we're subtracting is negligible. So now I'm going to solve this. First, I'm going to multiply both sides by 0.1. Cancel that out. And then I will take the square root of both sides. So I get 4.9 times 10 to the negative 11th equals X squared. Now I take the square root of both sides and I get X equals 7.0 times 10 to the negative 6th. All right, I need to check the validity of this. So make sure it's less than 5% of the initial concentration. 7 times 10 to the negative 6 divided by 0.1 times 100% equals like 0.007%. So that's super tiny. It's valid. So this is indeed X, the concentration of the hydronium ions. So if the concentration of the hydronium ions at equilibrium is 7.0 times 10 to the negative 6 molar, then the pH is the negative log of that, which is equal to 5.5. A pH of 5.15. A pH of 5.15, which is about what we'd expect. It has 10 to the negative 6. We expect it to be between 5 and 6. Notice, I'll just remind you guys to notice that the question asks find the hydronium ion concentration, but I used hydrogen in the problem. It doesn't matter. They are equivalent. So I guess the way to really write this equation out, I'll do it over here, with hydronium would be HCN plus water, liquid water, reacts to form H3O plus Cn minus, all right? But the water is liquid, so it won't be in the equilibrium constant expression anyway. So the equilibrium constant expression is the same. So whether you use hydronium or hydrogen, it does not matter. Okay? Next page. This is a problem that I intended for you to try, and I would walk around and check your work, but I can't do that right now. So please feel free to pause the video and try this yourself and then check your answer. So I'm just going to write it out. First thing I'm going to do is write out the equation and the Ka. So when this acetic acid dissociates, what's popping off is this H on the end. That's the hydrogen that's being lost. The Ka for this, when I look it up on a table, is 1.3 times 10 to the negative fifth. And now I can do my icebox. So we start with 0.25 molar of the acetic acid. It's going to go down by some amount. Each of these will go up by some amount. So at equilibrium, we'll have 0.25 minus X, X, and X as our concentrations. So we can plug that into our equilibrium constant expression. Since we know the equilibrium constant is 1.3 times 10 to the negative fifth. And its products, X times X, or X squared, over the concentration of the reactants, 0.25 minus X. I'm going to use the X approximation technique because this is a pretty small Ka, and we're going to say that that's not significant. And now we just need to solve. So multiply both sides by 0.25. And I get, gotta correct myself. This is 1.8. Misread, typo in my notes. 1.8 times 10 to the negative fifth. All right, now we can do the math correctly. So 0.25 times 1.8 times 10 to the negative fifth is 4.5 times 10 to the negative 6 equals X squared. Now I take the square root of both sides, and I get X equals 2.12 times 10 to the negative 3. And so that is our concentration of hydrogen at equilibrium. Oh, first I should double check the validity of this. 2.12 times 10 to the negative 3 over 0.25 times 100% equals 0.8%, so that is valid. Okay, so this X is in fact our concentration of hydronium. So our answers here are that the concentration of hydrogen or hydronium ions is 2.12 times 10 to the negative third molar at equilibrium, and the pH is the negative log of that, negative log of 2.12 times 10 to the negative third, which is equal to, should be around 3, and it is in fact 2.67. Okay, so we found the hydronium ion concentration, and the pH, using that icebox technique that hopefully you've mastered from the past chapter and are just applying here. All right, so just like in the equilibrium chapter, we could find equilibrium concentration if we knew the Ka. We could also find the Ka if we knew the equilibrium concentration. So that's what we're going to talk about next. We're going to talk about finding the equilibrium constant Ka for an acid from the pH. And we do this we're basically doing what we did before, but backwards. So instead of using the icebox to find the pH, we're using the pH to find the concentration of hydrogen or hydronium at equilibrium and plug that into the icebox, and then use those equilibrium concentrations from the icebox to solve for K, or Ka, as it were. So let's do an example problem. A 0.2 molar weak acid, again this generic one, HA, has a pH of 4.25. Find the Ka of the acid. So we don't know the identity of the acid. We can't look up the Ka value. It's asking us to find it based on the pH and the known initial concentration. So the first thing we want to do is always write out the equation and create an icebox. So for this acid, HA, it's going to dissociate into H plus and A minus is the anion, and our icebox set up here. So we have 0.20 molar initially of this and none of this. And at equilibrium, we don't have the equilibrium concentration, but we do know the pH, and we can figure out then what this equilibrium concentration is from the pH. So we can do 10 to the negative pH, 10 to the negative 4.25 equals our concentration of hydronium, which is going to be 5.6 times 10 to the negative 5. So that is our concentration here of hydronium at equilibrium, 5.6 times 10 to the negative 5 molar. Okay? In other words, this is our X. So this was down by X, and this is plus X and plus X. This is our X value. So that means that the concentration of A is also 5.6 times 10 to the negative 5th at equilibrium. And the concentration of HA is 0.2 minus 5.6 times 10 to the negative 5th. But that's still, if you type it in your calculator, still going to round to 0.2. That's such a small number that you're subtracting. So these are our equilibrium concentrations. And now we can plug these numbers, these values, into our Ka expression. I kind of did step 2. I just realized that. So I said use the pH to solve for X to solve for the concentration of hydronium ions, which is what I did right here. So now we're going to use these values and plug them in on the next page because I don't have room. Actually, I do have room, so I'm going to do it right here, but you might want to do it on the next page. All right, step 3, it says, is to plug in the equilibrium concentrations in the equilibrium constant expression. So the equilibrium constant expression for this would, of course, be H plus times A minus over HA. So we plug in the equilibrium concentrations that we just calculated. 5.6 times 10 to the negative 5th times 5.6 times 10 to the negative 5th is the same thing as squaring that, divided by 0.2. We plug that into our calculator, and we get 1.58 times 10 to the negative 8th. That is the Ka for this acid. And a question might go even further as to ask you what is the identity of the acid, in which case it wants you to go reference the table and find which acid has this Ka value, which you could do. All right, so the next page has a problem that I want you guys to try on your own. So pause the video, try it, and then watch and see if you get the correct answer. right, so now I have my equilibrium. I use the pH to find the equilibrium concentration of hydrogen, which is going to be equal to the equilibrium concentration of the A- ion, and these are all molarities. So now I just plug it into the equilibrium constant expression to solve for Ka. 8.9 times 10 to the negative fourth squared over 0.175, and I solve a Ka value of 4.54 times 10 to the negative 6. Remember, equilibrium constants, Ks, do not have units, so it is a unitless answer. So we said that weak acids tend to have very small Kas like this. And another way of sort of saying that is anything that has a small Ka, it means that the products predominate. The reactants predominate. So there's very little product that's produced. And so sometimes when we're talking about acids and their strength, we want to talk about how much product, or in other words, how much H plus they produce. And one of the ways we can do that is by reporting the percent ionization. What percent of this acid is ionizing, is becoming product. And we can do that as follows. So the percent ionization is the concentration of the hydrogen ions produced at equilibrium divided by the initial concentration of the acid times 100%. All right, and this math is going to seem familiar. So for the previous two questions, both of the questions we were calculating, we found the hydrogen ion concentration and we were given an initial acid concentration. So for that first one, we calculated it to be 5.6 times 10 to the negative fifth was the concentration of the hydronium ions, and the initial concentration was 0.2 molar. So the percent ionization there, I should say times 100%, is 0.028%. And then in the second problem, we had 8.9 times 10 to the negative fourth. And the initial concentration was 0.175 times 100% is 0.51%. So notice that both of these are still a very small percentage. It's a very small amount of ionization that occurs with weak acids. Most weak acids actually will dissociate less than 5%. They'll have a percent ionization of less than 5. So let's do one for a practice problem. Let's find the percent ionization of a 2.5 molar HNO2 solution. Right? HNO2 is not one of the 6 strong acids, so we can assume it's a weak acid. HNO2, when it dissociates, it's going to pop off that hydrogen, and then the anion that's left is NO2, 1 minus. And we can look up the Ka for this on a table, and we find that it is 4.6 times 10 to the negative fourth. And now we can set up our ice box, ICE. The initial concentration is 2.5 molar. This goes down by X, these go up by X. So at equilibrium, this is 2.5 minus X, and this has each of these has a concentration of X. So in our equilibrium constant expression, the Ka is 4.6 times 10 to the negative fourth, and our concentration of our products is X times X, which is the same thing as X squared, and the concentration of the reactant, 2.5 minus X. Since this is pretty small, we're going to assume that subtracting X, that X is so small that that's going to be negligible, so we're using the X approximation technique. And we solve for X. So I'm going to multiply both sides by 2.5. That will cancel out, and then I'm going to take the square root of both sides. So I get X equals 0.0339. All right, so this is my concentration of hydrogen. So to get first I need to check whether this is valid, right? I use the X approximation technique, so I need to check whether it's valid. So I do 0.0339 divided by the initial concentration of 2.5 times 100%, and I get 1.36%. Notice that my check for validation technique is the same as the percent ionization equation. So when you check whether your X is valid, you're actually calculating the percent ionization right there. So we're actually done with the problem. Just in checking that X approximation technique, we also simultaneously calculated the the percent ionization, which in this case was 1.36%. All right, so the moral of the story is that when you do that validity check, that is the calculation of the percent ionization. So in this problem, it was 1.36%. So here's a problem for you to try, and I will do it simultaneously, but feel free to pause. The first thing is we want to write out the equation. H is going to dissociate into H plus and NO2 minus. And we form the icebox. So initially we have 0.25 molar of this, none of this. So 0.25 minus X, X, and X at equilibrium. We can look up the Ka value. This is the same acid from the previous problem, so it has the same Ka of 4.6 times 10 to the negative 4. So 4.6 times 10 to the negative 4 equals X squared, X times X over 0.25 minus X. We're going to use the X approximation technique and assume that this is negligible. And so we multiply both sides by 0.25. And we get 1.15 times 10 to the negative 4th equals X squared. Take the square root of both sides, and X equals 0.0107. We need to check if this X approximation technique is valid, and also simultaneously calculate the percent ionization by doing 0.107 divided by the initial concentration of 0.25 times 100%, and we get this equals 4.3%. So the percent ionization here is 4.3. Percent ionization is 4.3%. So something interesting to note, if we look back at these two problems that we just did, we used the same weak acid, HNO2, for both problems. In one we had a 2.5 molar solution, and the other we had a 0.25 molar solution. So this one was 10 times more dilute, and this one was 10 times more concentrated. And we expect the more concentrated solution would have a higher concentration of hydrogen, which it did. We calculated this one to be 0.034 at equilibrium, and this one was 0.011